Hello, and welcome back to a video on MAT 1033 Intermediate Algebra. My name is Sean Perry. This is the video number 46 in the series, Dividing Polynomials by Factors. We've talked a lot in previous videos about how to add, subtract, multiply, and factor polynomials, amongst other things, but we've notably left out any talk about division of one polynomial by another. Before we jump into the idea of dividing polynomials by polynomials, in its full generality, we should remember some of the basic patterns from division of whole numbers. One of the first ways that we're taught to conceive of division is in the case when one number divides into another evenly, that is to say, with no remainder. This is the way that division works when we divide a number by one of its factors. Let's recall an example to make sure the pattern makes sense. Now, two of the factors of 12 are 4 and 3. 12 is equal to 4 times 3. And as such, if I divide 12 into 3 equal parts, those parts will be of size 4. Likewise, if I divide 12 into 4 equal parts, then each one of those parts will have 3 elements to it. We also could write this division in sort of this fraction form over here. I will make no distinction between these two forms because both of these symbols, the quotient bar and this quotient symbol here, just mean division. They are identical, so we will go back and forth between them freely. You can see nicely in this form the cancellation of a matching number on the top and the bottom being divided to get 1, and then 1 times 4 is just 4. Now from this example, we can generalize to get a rule or a property. If a number factors as a equals b times c, then we know two quotients at least. A divided by b is equal to c, and a divided by c is equal to b. I feel like that's important enough to merit some critical notes, so copy this down, show it to me later as proof you watched the video. If a is equal to b times c, then a over b is equal to c, and a over c is equal to b. Make sure you can see this by writing a as b times c and looking for cancellation by matching the top and bottom factors. Again, we will make no distinction between these two sets of symbols. A over b or a divided by b, they mean the same thing in all of the contexts we're going to be looking at. Now, this is the pattern that we're going to use to begin extending division to the polynomials instead of to just the numbers that are the 0th degree polynomials. Let's take as a first example the polynomial x squared plus 6x plus 5. We saw in previous videos how to factor this as x plus 1 times x plus 5. So right off the bat, I know two factors. I know that if I were to divide this by x plus 1, the x plus 1s would cancel and leave me only x plus 5. Likewise, if I was to divide this by x plus 5, the x plus 5s would cancel after factoring and leave me with just x plus 1. So it seems like we're saying here by this chain of inequalities that this quotient is equal to this new polynomial x plus 5. And that's true for all x's except 1. Specifically, for this first polynomial, this first ratio of two polynomials, this is true except when x is -1. And likewise, in this second ratio of two polynomials, this is not true when x is -5. Why is that? We often gloss over this little extra term here, that x must not be equal to -5, even though now this just looks like x plus 1. However, this should not be glossed over. We cannot have x equal to -5, or else this denominator would become 0. And then we would have something that looked like, well, 0 over 0 canceling to 1. Recall that 0 has no reciprocal. You cannot divide it by itself and have it be equal to 1. 0 divided by 0 is an undefined expression. It is not 1, and so it does not cancel. The consequence of that is that when we do this kind of apparent cancellation, we have to keep track of the fact that this was only true if x was not equal to -1, or in this case, if x was not equal to -5. This cancellation is not true in the case where we would have a 0 over 0 situation. Now, when we were dividing by numbers, it was pretty easy to check that we weren't dividing by 0. A number either is 0 or it isn't 0. If it is 0, you can't divide by it. If it's not, you can divide by it freely. So it wasn't that hard to avoid when we divided by numbers. But now we're dividing by expressions. We have expressions involving x, a variable. And so depending on the value of x, that expression might be able to equal 0. It might equal 0 in several places. It might equal 0 in no places. But we're going to be looking, when we divide by polynomials, at situations where x might have some finite number of zeros. It depends on the value of x that we plug in. Here's something I think merits a critical example. I want you to copy this down for your notes. Is x over x equal to 1? Well, it is in almost all cases. Let's look at the graph of these two functions, both 1 and x over x, to see the difference. X over x is equal to 1 except when x is 0, in which case we have 0 over 0, which is undefined and not 1. We must leave that out of our domain. We must leave this point out of the graph. It actually is not defined there, and as such, there is a hole. It's very difficult to show just leaving a single point out on most graphs, so we depict it by this big open circle to show us that there is a point that has been removed right here. On the other hand, if we look at the graph of y equals 1, that's just the flat line at y equals 1, level, zero slope line. Now, the issue here is that, well, there is a value. If you plug in x is 0 here, you still get y equals 1. Nothing has changed in that context. And so we can see that these two are almost the same. They are in fact the same everywhere else except for 0. While this one is defined as 1 at 0, y equals 1 is defined as 1 at 0, this one is undefined at 0, x over x is undefined at 0 for x, and so we have a hole at this value, 0, 1. So no, they are not exactly the same. They have a key difference between them, and it has to do with dividing by 0. Now, this whole section, this final section in the course, is going to relate to dividing polynomials by polynomials. These are the so-called rational functions. They are ratios of two polynomials. They are quotients of two polynomials. One of the main activities we will be doing is factoring our polynomials, canceling their common factors, and keeping track of where those factors would have been 0. At any point where this cancellation happened, and we would have had one of the factors in the denominator be 0, they actually don't cancel exactly. We have to leave that out of the domain. In fact, we had to leave it out of the domain initially too. Rational functions are not defined where their denominators are 0. I actually think that merits one last set of critical notes. Let's define the rational functions. A rational function of x is a quotient, p of x divided by q of x, where p and q are both polynomials. The function of x is undefined, where the denominator q of x is equal to 0. You cannot divide by 0. These points, these x's, which would make q of x equal to 0, are restricted from the domain of r of x. We must omit them to define r of x as a function. So as we learned before, the first move that we make when we factor should be to look for a greatest common factor in each and every term in your polynomial. And that's going to be one of the main ideas about canceling that we can do in order to easily divide one polynomial by a monomial. Here is an example. Let's say I wanted to divide this polynomial here, 3x to the 5th plus 9x to the 4th minus 12x to the 3rd, by this polynomial here, 3x to the 3rd. What I should do before any attempt at factoring of any polynomial is I should look and see if I can pull out a common term from each one. We look at the coefficients and notice that 3 is the greatest common factor. We look at the x's and we notice that our smallest exponent is 3. And so we notice that we could divide 3x to the 3rd out from our numerator polynomial and cancel it entirely with the 3x to the 3rd on the bottom. This would leave me just the x squared plus 3x minus 4. And we must keep in mind that x could not be 0, because that would have made 3x to the 3rd 0, and that would have been disallowed. So keep in mind, even though it now looks like we just have x squared plus 3x minus 4, which doesn't seem like it has any problems with plugging in 0, you plug in 0 here, you get minus 4, no problem. However, we got here by dividing by 3x to the 3rd. And 3x to the 3rd is going to be 0 when x is 0, and thus it must be left out of the domain, even in this resulting function, which doesn't seem like it has a problem there. It is not an allowed value. If you plugged in 0 into this, it would be disallowed and you would get undefined still. All right, let's take a look at another simple case, one where we divide by linear factors. The first thing we should do after we try to factor out the GCF is to try to factor the polynomial into linear factors. This is what we did when we used the AC method, or looking for the sum of two factors which equals the middle term in trinomials. So let's look at this one here as an example. Notice that it's not a quadratic. It is a trinomial, but it's not a quadratic trinomial. And so you might think, well, I'm kind of out of luck. If it's going to be a cubic, I only know how to factor by grouping. Well, but remember, try to factor your greatest common factor out first. A 2, a 14, a 24, we could pull 2 out of each one of those, and there's an x in every term, so I could pull that out too. Now that you do that, what remains is a quadratic trinomial, and it can be factored. We set up the parentheses, and we notice that 12 has factors 4 and 3, which sum to be 7. Now that does cancel with our x plus 4 on the bottom, and we're left with just 2x times x plus 3. Keeping in mind, of course, that x could not have been minus 4, because that would have been the x which makes this denominator equal to 0. Okay, let's move on to some praxis. Let's do some practical exercises for today. Simplify and state the domain restriction. That's the x values that you must not let the denominator be, lest you get a 0 there. So give these a shot. Pause the video at this time, factor, cancel, and see what remains. Okay, let's see how you did. The first one is pretty straightforward. We factor the numerator. It cancels one of its factors with the denominator, and we're left with just x plus 4. We must keep in mind the domain restriction, which is that x cannot be equal to 7. For the second one, we repeat the process. This time, we factor out the greatest common factor, and perhaps what remains does factor, but we are canceling everything from the denominator here because the denominator also has a 2x squared in it. So once we factor out the GCF, we can cancel completely, and we get this remaining quartic trinomial. We keep in mind, of course, that x could not be 0, lest the denominator be 0. Finally, let's look at one that doesn't cancel completely. So if I factor x squared plus 2x plus 1, that's a perfect square trinomial, and we get x plus 1 squared. On the bottom, that's the difference of two squares, so I get x plus 1 times x minus 1. The x plus 1s, or at least one of them, cancels, and we're left with a single x plus 1 on the top, and x minus 1 has nothing to cancel with it, so we just get that on the bottom. Now, even though this denominator here only has a problem with x's positive 1, x's minus 1 is also removed from the domain because this would have made the original denominator 0, which is disallowed. So we have two items of domain restriction here. X cannot be 1 and x cannot be minus 1. But in all other places, it looks like this rational function here. All right, that's it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.